All right, guys, hi. Today we're going to look at graphical analysis of motion. Most textbooks start with the mathematical analysis of motion, but if you start with the graphical analysis, you understand where the equations come from to analyze motion mathematically. So the first of the graphs that we need to understand is a displacement time graph. You're looking at change in position on your y-axis and time on the x-axis, and it's an easy way to graphically represent motion. Here is something that is going fast. And here is something that's going slow. Here's something that might start slow and ends up going fast. Because the steepness of the line or its slope represents your speed or your velocity, that is where the first kinematics equation comes from. If you look at, it's really an average. If you look at your average velocity, it ends up being displacement over time. And that's the first big classic physics equation, velocity equals distance over time. Makes sense too, because if you look at the units, your distance is in meters and your time is in seconds, and so obviously meters over seconds is a representation of your distance versus time, or how fast you're going. Next one is a velocity time graph. Velocity time graphs look very similar. This object here that was going fast might look like this. And this object here that's going slow might look like this. And an object that starts out slow and goes fast ends up looking like this. And so this red line here is real important. If you start out slow and you end up going fast, you're accelerating. And so we end up with our second kinematics equation, acceleration. And acceleration would be your change in velocity over time. And formally, you would write that like this. And that is what I would consider to be equation number 2 for kinematics. Oftentimes it's written like this in terms of V2. But both of those are mathematically the same. If you analyze the units here, it makes sense as well. Your change in velocity is in meters per second. And if you divide that by seconds, you get meters per second, or meters per second squared. And so that makes sense. That is the dimensional analysis for acceleration. And the last of the 3 equations is an acceleration time graph. This fast object, it's not changing its velocity, and so we'd graph it at 0. Same with the slow object. But an object that ends up going from slow to fast, they have an acceleration. In this case, it's a constant acceleration because it's constant slope, and so we graph that like this. That would be the graph of this. Acceleration time graphs don't really get much analysis because oftentimes they're straight lines. These courses really give you uniform acceleration in most cases, and with uniform acceleration you have a straight line on a VT graph and you have a horizontal flat line on an acceleration time graph. But here's a real common multiple choice question. When you look at this quantity right here, the area under this line has meaning. We can determine that meaning by looking at the dimensions here of measurement. A quick dimensional analysis will tell us that your acceleration, which is meters per second squared, times time, which would be the area of this quantity, allows you to cancel out a unit and gives you meters per second. So the meaning of this area right here is a velocity, and it turns out to be your change in velocity. And so if you just know an object's acceleration, whether it's slowing down, speeding up, whether it starts at 0 or starts going fast or slow, you can get a change in velocity really quickly by looking at the area here. And you can actually do that on a velocity time graph. If you look at the area under a line for a velocity time graph and look at a dimensional analysis of it, you end up with velocity, which is meters per second, times time, which is seconds. And when you multiply those together, you're left with meters. You basically end up with displacement being represented by the area under the line on a velocity time graph, just like your change of velocity is represented under the line on an acceleration time graph. And so this is a little bit muddled, so let me just quickly review this. There's only 3 or 4 skills that you would ever apply with a motion graph. In the 3 graphs we just looked at right now, you're looking at a calculation of slope. If you wanted to know like where an object was or how fast it was going at a given time, depending on the graph, you could just read off the y-axis. If you wanted to know how long something took, you could read off the x-axis. And if you wanted to know either how far something went or its change in velocity, you're just calculating an area. And this is really important because it doesn't matter what the topic is. Anytime you're given a graph, there's only several operations you can perform. You can calculate the slope, it'll have meaning. You can calculate the area, and most of the time it'll have meaning, but not always. You can do a dimensional analysis to figure it out. Or you can just look at the x and y axis to read information directly off. And so that's a really quick review of, or introduction to graphical analysis. Now I'm going to show you some tricks while reading graphs. All right, so here are two graphs. When you're trying to analyze graphs individually, a displacement or a velocity time graph is pretty easy, but it gets very confusing once you start mixing the two together, because one thing on one graph is not the same meaning in another thing on another graph. So I've got two graphs here. They do not represent the motion, like the same motion of one object. They're two totally different objects. It's just that the graphs look the same. You want to be able to answer questions related to these topics anytime you're given a graph. And so I quickly want to run down these topics and figure out how to answer questions from each of these topics with respect to each of these two graphs. These are real common multiple choice and free response questions. The first one here is constant velocity. You should be, it's an easy question, but students make the mistake all the time. You should be able to determine where the velocity is constant in both of these graphs. The velocity is constant here because the object is, oh, that's a mistake. I made the exact same mistake. The object is constant here because you have a constant slope. And the velocity is constant here because you have a continuous slope. And you have a constant velocity here. The mistake that I made is that there's no velocity here, except that if you look at the VT graph. If you look at the VT graph, it's totally different. You end up with constant velocity here and constant velocity here, but you have changing velocities in between them. And so, I mean, it's simple individually, but when you start putting the graphs together, it's easy to mix up. I made a mistake on the first one. Next style question you need to be able to freestyle with is determining when an object is at rest. Objects are at rest when they're not changing position. And so if you look at this position time graph, right there is an object at rest. This object is also at rest right there because it's not changing position. Well, that's very different when you look at a velocity time graph. This object might have been at rest right here where it started because the velocity is 0. But it does not correlate to the top. That's when it's going the fastest. It comes and slows down and goes to rest right there, where velocity is equal to 0. And then there might be a third situation here where this object is at rest, and right here, it would be when the velocity equals 0. And so you can see pretty much an inverse in the way that you read displacement and velocity time graphs. You've got to be careful, you've got to know the difference. Next scenario here, when an object is speeding up, that's hard to see on this. This doesn't represent a change in speed. These are sort of instantaneous changes. But you can see where an object's speeding up here. If we call this one number 3, an object is speeding up here and remains at constant velocity. And then it slows down here. But this is interesting. It's speeding up underneath the x-axis. As you cross through this here, your velocity is 0, and that's what this 2 represents. And then it starts speeding up, but in the negative direction. So speeding up here, coming across, and then it slows down right there. And so we're going to put numbers on slowing down. We'll call this number 4. This object slows down here, and it slows down here. Even though these have opposite slopes, this is just slowing down going backwards, which is positive acceleration. And this is slowing down going forward, which is the negative acceleration. Looking at the next one, a classic question is, where is an object back in its original position? And so, because of the symmetry of this graph, you can see that the object moves forward, comes back where it started, goes backwards, stays there, and then ends up sitting still at its position, well, presumably. In that case right here, where is its position? The same as where it started? Well, it comes back to where it started right here. And then it comes back to where it started right here. Because it's position 0 right there and right here. That's a little bit different over here. You'll remember that displacement is measured by the area of this. And so when your forward area, all this forward motion, when that forward motion equals your backwards motion, which would be all this, you are back at your original position. And so I hypothesize that if these two were equals of each other, that you'd be back at your original position right there at number 5. Looking at displacement, determining the displacement. If you have to look at the displacement off of an xt graph, you just read it off the side. Right there, whatever that value of y is the displacement. It stays constant. And then there becomes a displacement when you go from here to here. You just read that information off the y-axis. It's your change in the y-axis. But over here, displacement we've already got in red. The area represented here is forward displacement. The area represented here is backward displacement. But the distance is a little bit different. You have to understand the difference between distance and displacement in terms of vector and scalar quantities. But because distance is a scalar, it's all just positive values added up. You move this distance of x plus this distance of x as you get here, plus this distance of x, and then plus this distance of x. There's 4 distinct displacements or distances that you would add up to get the total distance covered. But the displacement actually is 0 on this one. Or it might be approximately 0, because you go forward, then you go back, and then you go backwards, and then you go forward, and you end up at the same spot. Looking at the displacement covered here, if this is a positive quantity and this is a negative quantity, it could be that the displacement is 0. But the distance here, these would both be positive quantities. You have to add them up together. And then this is a great trick. You can determine average values. If I want to know what my velocity is between this point in time and this point in time, it's the slope of that line. So you go fast and then you don't go anywhere at all. But if you want to know the average velocity between this point in time and this point in time, you can connect dots at any point and they give you averages. And so right there, the slope of that is your average velocity, your change in position over time. So what does the average velocity say in the first 5 seconds? Well, it is the slope of the line that connects your position in 5 seconds with where you started from. There's a nice way to calculate averages over here, and it's very intuitive. It's basically the midpoint of this line. So if this object accelerates from 0 and then is going at 10 meters per second, you can look at the midpoint for that and say that on average in this whole area you end up with 5 meters per second as an average velocity. And so being able to calculate average values is really important when it comes to freestyling on difficult multiple choice questions, because if you can turn changing values into an average, it allows you to take multiple values and just treat them as one, and it becomes easier mathematically. And I'm sure we'll look at examples where we do that a lot. Okay, now for some practice problems. All right, so here are 2 common, pretty looking motion graphs. The first here on the left is a displacement time graph or position time graph. The one on the right is a velocity time graph. And here are some pretty classic questions that you need to be prepared to answer. We'll ask the same question for both graphs, and you'll see how we're using the same skills, but you use them a little bit differently depending on which graph it is you're working on. So the first question is, when is the object at rest? Well, the object is at rest when its position is not changing, and so between the 3rd and the 6th second here, when the time values are between 3 and 6 seconds, the object is at rest. That's a little bit different over here on the velocity time graph. On the velocity time graph, we start already moving at +4, so moving forward, then slowing down, coming to a stop right there. Between the 8th and the 12th second, that's likely to be at 10 seconds. So at 10 seconds, the object is at rest. What is the velocity after the 4th second? Well, after the 4th second, the velocity over here, there's 4, is 0. The object's not even moving. So velocity is 0. But over here, after the 4th second, we still are moving 4 meters per second forward. And so you can see 4 meters per second. Now, what is the acceleration after 10 seconds? Over here, moving forward, stopped, moving backwards, and then moving backwards, but not quite as fast. There is no acceleration happening here. You could argue that there's acceleration occurring right here at these changes of velocity, but in most cases that's not the case in a question. But at the 10th second, over here, the 10th second is right between the 8th and the 12th, and there absolutely is an acceleration there because velocity is slowing down, coming to a stop, and then speeding back up. Even though the velocity is 0 there, it still is undergoing an acceleration, whatever this object is, and so we need to figure out the slope of that line. We can do it from the whole value, or we can do it from just half of the value. I think that's what I want to do. This right here is downhill, so it's going negative, and it goes down 4 units, while it runs 2 units there between 8 and 10. And so that slope would be -2. And so no acceleration here at 10 seconds, but on the 10th second here, we are going -2 meters per second squared. What is the displacement after 12 seconds and also the distance? So distance first here, the total distance covered after 12 seconds, the object goes up 3, then comes back 3, then moves all the way out to -6, and then not moving as fast, but ends up at -8. We've got to add all these numbers up together. It's distance, and so they're all positive. And we take 3 and 3 plus 6, 12 plus 8. I think we've got 20 total meters. But the displacement, you have to include forward and negative. And basically, if you took 3 plus 3 plus -6 plus -2, you'd end up with a negative value, and we can sort of cheat that math. It's just from where you start to where you end, and if you start at 0 and end at -8, well, between 0 and 8 is a displacement of -8 meters. A perfect example of how distance and displacement can be the same thing. When we look over here, the total distance covered is the representation of these areas. We've got this big rectangle, we've got this triangle, we've got this triangle, and we have, whoops, that's actually this triangle, but they would be the same distance. And then we have this last big rectangle. And so we need to sum all those values up. And here is a 4 times 8, that's a 32. And then we've got this little triangle right here, 1/2 base times height. Its height is 4, its base is 2, so 4 times 2 is 8, and half of that is 4. So 32 plus 4. Now, these are symmetrical, so we have the same region there. It's another 4. And then lastly, this last one is probably the same size as here, and it is, and so that same value of 32. What is this? 64 plus 8 for 72. 72 total meters is the distance, but that's not the case with the displacement. In this case here, these are both positive values, so you have a 32 plus a 4. And then the next 2 regions of space are negative values. And so basically you'd have -4 times 2, and you'd have -4 times the difference of 20 and 12. And so that adds up to 0. The displacement is 0 in this scenario, even though the distance is 72 meters. When is the object at rest? Well, we're at rest here, and that's it between, oops, repeated question, quick, to the last one. So when does the object pass its original position? Well, this object starts at 0, on the displacement time graph moves out to 3 and then comes back to 0 right there. That is somewhere between the 6th and the 9th. We'll approximate it to 7.5 seconds. The 7.5 second it is at 0. And then over here, when does the object pass its original position? It's when the positive values equal out the negative values. And so there's all this positive displacement here, and then you have negative displacement here. Actually, on this 20th second, the object has gone forward, slowed down, come to a stop, sped up in the negative direction, moved at constant velocity, and after 20 seconds, it's right back where it started from. And so the 20th second occurs when the object is at its original position. Look at some past problems here. This is an old AP question. We have a displacement time graph, and the question is, what is the average speed between the first and second second? On any of these curvy graphs here, you can cheat a quick average by just connecting the beginning to the end, and the slope of this line averages out the lower slopes here and the larger slopes there to be this average slope. So this question is asking about the slope between the first and the second second, and so if we draw a line right there, we would see a slope of up, it looks like 6 and over 1, and so the correct answer would be 6 meters per second between the first and second second. Second question here, also an old AP question. We're looking at the displacement of an object here. The question on a VT graph is, when does the object pass through its initial position? And so it starts off at rest, but it quickly accelerates backwards, and so this area right here would represent the displacement backwards. And it's going to pass through its initial position when the displacement forward is going to equal the displacement backwards. And so if we look at this right here, at that point, I would say these two regions of space are about equal. And so between the first and the second second is when this object is going to pass between its initial position. Next question here, old IB question. We have a VT graph, and the question is, what is the total displacement after 1.5 seconds? And so displacement off of VT graph is area, and we're looking therefore at the region of space indicated there. And so it moves forward for a while. It starts out fast and ends up at a stop, and then starts to move backwards. And there's the first full second. Now, something that's important to note there is that these are going to end up canceling each other out. We have forward displacement and backwards displacement, and they're both the same magnitude. And so the answer here that we're looking for is going to end up being represented by this region of space right here. We want to know that. I'm not sure why it's not drawn in there. There we go. And so this is a triangle. We've got 1/2 base times height. Height 5, base is 0.5, so 1/2 of 5, 2.5. And then times 0.5, 1.25. Correct answer would be B for this question. Third question here, old AP question, XT graph, and the question is, at what point is the acceleration, or what is the acceleration of this object? And because it's a straight line, it means it has constant velocity. There is no acceleration. And so we'd be looking for an answer of A, 0 acceleration. Here's an old IB question. We have a velocity time graph. And before I even look down here at the bottom, my problem solving strategy is to interpret what's going on here in this graph. And so just looking at it right here, I have an object that starts basically at rest. There's no motion. And then it's going really fast up here, and here, back to 0. So it's going from 0 to fast to 0. Now we're trying to match a displacement time graph to it. The question is, which graph shows the distance traveled? Well, this right here represents constant velocity forward, and the velocity up top is always changing because the slope is changing, and so bad choice. If we take a look at C here, this one is an exact match of the graph above, and it would be pretty rare that that would be the case, but to analyze this right here, this would represent fast, and this over here would represent also fast, but in the negative direction. And so this is going fast to basically 0 and fast. And that's the opposite of what we're looking for, so not a good choice. D looks okay. It's curvy, and oftentimes nature gives curvy graphs. Because the slope is large here, this goes from fast to a 0 value and then fast. And that's not what we wanted. And so it looks like B, by process of elimination, is going to be our choice. But to quickly analyze it, what we've got here is an object that starts going slow, and then it's going fast because of the large slope, and then it ends going slow. And that's basically what we were looking for that we identified earlier over here. And so B would be the correct answer. This is an interesting question right here. It's a little bit awkward because there is an acceleration time graph with a value or magnitude that is always changing. And that doesn't really work with any of the equations we have for kinematics. And this requires one of the cheats that we've discussed at some point. And that is taking a changing value and just turning it into one average value. So if this acceleration starts at 5 and it ends at 0, I think it's pretty safe to say that the average acceleration during that time is 2.5. And so the whole time that it accelerates, average acceleration approximately 2.5. Well, the question here is, what is the speed of the car after 3 seconds right here? And so basically, we've got a new graph. It's 2.5 acceleration and 3 seconds. And acceleration times time from one of our tricks is the magnitude of this value right here, the area of that triangle. And so we can just multiply 2.5 times 3 and end up with, well, it looks like they're thinking it's 3 times 2. 2.5 times 3, I would argue that that probably is closest to 6, but it's not exactly 6. A little awkward there. Next question here. Girl goes for a walk. She stops after moving forward, and so these all look pretty good. And then she goes faster than she originally had. So we've got moving forward, stopped, and then even faster. We can start to eliminate choices here. This is not a good choice because this is faster but going backwards. This one here is not as fast as this one, and so that's a bad choice. Here's moving forward, stopped, going fast, so this looks pretty good. This is moving forward, coming to a stop, going backwards. Let's take that out. Oh man, I think we've already found the right answer. Let's just double check. So the second velocity is greater, and then all of a sudden, oh man, all of a sudden she turns around and walks quickly back home. So I was pretty excited to eliminate this one, but I think we made a mistake there. There is a stop, and there is a slow part, but then it goes faster here. And this goes then quickly all the way home. This one is quickly all the way home, but this part here doesn't work for us, and so we're going to take this as our correct answer. Almost done here. Dropping a ball from a large height. It's a beach ball, so large volume, low mass. This includes air resistance, though it doesn't state it explicitly. This would be constant velocity, choice A. Don't like that when I drop a beach ball. This would be slow velocity, increasing faster and faster and faster. That would look pretty good with without air resistance. This one here represents slow and then a constant final velocity. That actually sounds pretty good because the ball would be reaching terminal velocity, so I like this one better than that. I'll eliminate this. This one here starts out slow, or starts out, sorry, at 0 velocity, and then slows down, and it's moving towards a constant large velocity. And I realize when I say that I've misinterpreted this. This one here is changing velocity constant at increasing rates, so we're going to kill that. I'm liking this choice so far. This one here has a constant increase in velocity and then constant velocity. So these two are similar to each other, but this would be far more likely to happen in nature, where terminal velocity is reached sort of slowly, not really abrupt. So correct answer is this one. And then lastly right here, we have an acceleration time graph. Again, changing values, which is a little bit weird. The question is, what time would the car be at its greatest velocity? So this object speeds up in the positive direction, and so I guess it doesn't matter whether it's positive or negative. However, this is in the positive direction, and so it's going faster, faster, faster. Now, the acceleration decreases, but it's still accelerating the forward direction, and so it's going faster and faster and faster all the way up to the 4th second. At this point, acceleration becomes negative. So assuming it was moving in the positive direction with a negative acceleration, it's starting to slow down. And so it slows down, slows down, slows down, slows down with greater magnitude of acceleration. So I think that it sounds pretty good that the greatest velocity occurs in this region right at that 4th second, before the point where it starts to slow down. So I would take 4 seconds for this one. All right.